So today it is my pleasure to welcome Johan Ugander from Stanford University to the CAM Colloquium. So Johan's a professor in management science and engineering. He does a bunch of really awesome work in social networks, social choice, causal inference, experimental design. Just one example of a really cool piece of paper that he did was this work on 4 degrees of separation in the Facebook social network, which I think he did as a graduate student here, that won a Best Paper Award. And perhaps the greatest thing about Johan is that he did his PhD in CAM and graduated in 2014. So we're very happy to welcome him back. And with that, I'll let him start his talk.
It's all been downhill since then. Thank you, Austin, for the introduction. It's great to be here virtually. When Austin originally extended this invitation, it was supposed to be a real world thing in the spring. That didn't happen, and now we're sort of like all come to terms with the new normal. So I will do what I can. It's really a shame to miss out on an excuse to visit Ithaca. I actually haven't been back since defending my thesis, which life happens. I've had 2 children, and so travel has become a lot more difficult. But I look forward to making it to Ithaca in the near future, whenever the world allows. So in my talk today, I'm going to talk about work that is essentially all kind of work that began right at like an interest of mine that developed just as I was finishing my thesis, which was on kind of these problems of discrete choice. And it's been just a very fun sort of line of work that I've had a lot of fun working on. There's a lot of interesting questions, and I think that I've teed up something that will make this work feel very applied mathy, so very sort of like friendly to an applied math audience. It's work with some great collaborators. Stephen Reagan and Arjun Seshadri are 2 of my PhD students. Roel Makajani was also a Stanford PhD student who worked with me on a project. And Alex Pesakovich is a collaborator that I've had for a number of years at the Facebook AI lab in New York. So discrete choice with irrelevant alternatives. We'll come to define what an irrelevant alternative is. Let's start by saying, what is discrete choice? So we're choosing things, and we're choosing things from sets. That's going to be the name of the game today. The classic problems in this area that motivate the work in this area are work by McFadden in transportation. So you're trying to get from A to B, and you're deciding whether you should drive a car, go for a nice bike ride, whether you should take public transit, whether you should call an Uber or Lyft, and sort of you're making a choice between this from a set of alternatives, sort of what mode of transportation to take. Another like early motivating problem was these problems of whether to go to college or sort of what school, not just separate research area from school choice as a research area, but these decision problems of whether you choose to get a job versus go to school, and trying to use these models to understand the preferences that individuals have and how people value different alternatives. So you're choosing things from a universal set that we're going to just kind of call X, script X, throughout the talk. And at any given time, you're given a choice set C, which is a subset of alternatives. Now there's a deterministic version of this problem, which is that we're trying to understand, a person is a map from sets to elements. It could be like a very deterministic mapping. For every single set, one of the elements in that set is what they kind of like return in their mapping. That function itself is a very interesting object, and that function space is interesting. I'm going to focus this talk on the latter formulation, which is the probabilistic formulation, where we're going to allow there to be a distribution over all subsets of a universe. So we have 100 different, we're looking to buy digital cameras, and there's 100 different digital cameras. And every time you present me with 2 or 3 or 5 different digital cameras, I have a different little histogram in my mind's eye over the alternatives that you're presenting me. So The agenda for this talk is that I'm going to start off by talking about this mathematical object called choice systems, which is kind of the fundamental object of study in discrete choice, in probabilistic discrete choice. And then I'm going to talk about this assumption in discrete choice called the independence of irrelevant alternatives. This is not to be confused with the independence of irrelevant alternatives in social choice as it relates to sort of Arrow's work on Arrow's impossibility theorem, et cetera. This is more of a statistical statement than any kind of strategic statement. And what we're going to do is that I'm going to give you 3 different derivations of how you kind of can get to models or get to a single model, which is sort of like the model that exhibits the independence of irrelevant alternatives in discrete choice. And by taking 3 different derivations, I'm going to also give you 3 different deviations. So we're going to talk about models that step outside of this simplistic model class. And then as time allows, I'm going to give you the flavor of some additional work on how do you hypothesis test whether something obeys, whether a choice system or whether a person, a chooser, is obeying IIA. And I'm not actually going to give you a test, but I'm going to give you lower bounds on hypothesis testing and show you sort of how hard it can be depending on different problems. So what is a choice system? A choice system is it's a rare treat in math and applied math that you get to kind of like meet a new object. So you're all familiar with a bunch of these mathematical spaces. We have sort of the standard vector space Rn. There's the space of differentiable functions CK. There's binary matrices up there. Let me start being interactive with my pen here. We've got, nope, that's not what I wanted to do. I wanted to do this. We've got binary matrices, we've got the space of permutations, we have the simplex, the sphere. These are all spaces with their own, this is meant to be the sort of polynomials of degree n as a function space. These are all spaces, a lot of them are kind of traditional vector spaces. The choice systems, sort of as thing 1 is illustrating, they're this thing, understanding the structure of this thing is sort of its own very interesting project. So I want to give you a sense of what this thing is, and then what these modeling assumptions like the independence of irrelevant alternatives mean. So as a preamble, part of this dates, like sort of my presentation here dates back to a, for me, memorable camp colloquium when Megan Owen came to give a camp colloquium when I was a PhD student. She was herself a CAM alum, and she was talking about what's sometimes called Bellera-Holmes-Voigtman tree space, or BHV tree space. And BHV tree space is this quite beautiful half continuous, half combinatorial space over phylogenetic trees. So it's this, the entire talk was about how do you define means and variances in this space. In particular, you have a population of phylogenetic trees, and how do you define the mean as sort of like the point that minimizes distance to the other, sort of like depending on your norm and all these types of questions. And it was really an exercise in sort of like understanding the space. If I can get just one of you as excited about choice systems as I got about tree space. I never ended up doing any work or not yet, in this space, but I just thought it was like, it's a rare treat to get to meet a new object. So without further ado, just sort of like placing that in context. So what is a choice system? So what we're going to do is we're going to let sort of P sub xc be the probability of choosing x from a set C. So that's a discrete probability distribution. Its support is the size of the set. And what we're going to do is we're going to talk about the collection of probability distributions. I'm going to make this graphical in just a minute, but I just kind of want to put this in front of you. We're going to talk about the collection of these probability distributions over all sets that are subsets of the universe, and then sort of like, for every element. So it's all these little histograms. And the there's a qualifier here where I called this the conditional choice system. This is sort of like conditional on the fact that this is the set I'm serving up to you. What's the probability that you pick A, B, or C? Now, the use of thing 1 alludes to the existence of thing 2. So thing 2 in this world is sort of like the full choice system, is sort of the vocabulary to distinguish itself from the conditional choice system, which also considers, so I sort of, there was a magic bullet that arrived on the screen, which is here, which is, we have these weights that denote the probability of choosing from a set. So that's sort of the probability that there's some generative process that's sort of like handing you sets. And that itself is sort of something that you ordinarily condition on when you work with conditional choice systems. There's sort of to use economist speak, there's an exogenous process that's handing you sets, and you're just looking at the probability distribution over the set you're handed. Whereas when you're thinking about a full choice system, you're also considering some distribution over how sets are being queried. And that's going to become important in the latter half of the talk. So we're going to focus on thing 1. We're going to focus on this collection of distributions. And so let's consider this set ABC. Let's do something that we can do in Zoom world that's messier to do in an ordinary seminar. So let's consider all the subsets of this set. We're going to sort of say C1 is just A and B. We're going to say, C2 is just B and C. C3 is then the other pair. And C4 is the full sort of set equals. It's interesting that the screen doesn't exactly match what's on my iPad, but I'll deal. So those are the subsets that we're dealing with. I'm actually going to just kind of like clean up the screen a little bit. So we have these 4 sets that are kind of like all the subsets, the non-trivial subsets. We're not just going to look at elements. We assume that if you're just handed one element, that's the element you choose. So what we're then going to do is we're going to paste little histograms on each of these sets. And we're going to say, OK, if I give you A and B, you choose A and B with some relative probability. If I give you B and C, these aren't going to align horizontally. Maybe it's a 50-50 choice. And then I give you A and C, and you're like, oh, A is much better than C. Great. These are the 3 pairwise probability distributions. And then finally, we get sort of the distribution on ABC, where we have maybe a little bit of A, a lot of B, and a little bit of C. So the question is, this is sort of a collection now of 4 probability distributions. And how can we think of these as kind of like intertwined? We're trying to understand sort of the relationship between pairwise choices and setwise choices. Is there something about the way a person is making choices from the triplet that is sort of consistent with these pairwise choices? This looks strange. When I give them ABC, they're very likely to pick B. But then, I remove C, and that looks normal. Sorry, that's an example of something that like sort of looks normal. When I remove C, it looks like A and B still stick proportional to each other. Whereas if I remove A, all of a sudden, so I take this here, I cross out A, and so I'm basically sitting in this world. And if you look at it, the distribution over B and C looks nothing like the relative probabilities of picking between B and C in the triplet. This is just sort of like things that you can build up just from staring at histograms, that would be maybe something I'm sort of foreshadowing, that's something that you wouldn't like. Here's another way to sort of like, here's a way to think about these kind of interconnected spaces. So what I'm going to do is I'm going to draw the following diagram where I'm going to put A, I'm going to put B, and I'm going to put C on the corners of a triangle. And I'm going to say, you know, this space right here is sort of like the simplest line segment that's like the proportion with which I pick A and B. And I'm maybe going to say, I'm going to say that, you know, B, this isn't exactly what's represented in the histograms, or it sort of is, that B is chosen more often than A. Great. And then I'm going to look at one of the other line segments. So for B and C, I'm going to go 50-50. And for A and C, I'm more likely to pick A. And so those are sort of my three pairwise probabilities. And in the middle, I can draw kind of a, I can represent the three-way choice as a point that's like, you know, closer to B and otherwise split in AC. And so you can ask yourself, is there some way we can understand the ways in which the faces of this simplex somehow constrain, you know, if we're going to start making assumptions and make these choice systems non-arbitrary and start to make kind of behavioral assumptions, the way that the faces of this simplex constrain the probability distribution that's sitting sort of inside the simplex. This is my backup slide if my iPad wasn't working. So same thing, but just sort of like, you know, wear belt and suspenders. And now I'm getting activity here. So there's a question maybe?
Yeah, just checking if you're, so you're not assuming an outside option the way you're defining this?
No outside option. Yeah, thanks, Sid. Yeah, so this is the complete universe, and a lot of the use of choice modeling, there's sort of there's an alternative that hangs out always in the universe, which is sort of the outside option. But here I'm, you know, within a large universe, you would say that there's some like element that's sort of the outside option. But yeah, so I'm going to consider the outside option to be an option. Yeah, great. Are there any other questions about kind of like this view? This is not a standard view in any view. This is this like simplex view is something that for me has been an illustrative perspective. Any other questions at this time? Cool. I'm going to continue. So now this jargon that made its way into the title of my talk, this concept of irrelevant alternatives. So what I've talked about so far are just arbitrary choice systems. McFadden in his early work on discrete choice, so McFadden identifies as an econometrician, went on to win a Nobel Prize in economics for this work, or Bank of Sweden Prize. And in an arbitrary choice system, you're making, you know, no assumption on the relationship between distributions on different sets. There is, however, a very reasonable and powerful assumption that drives almost all work in discrete choice, or a huge, you know, one of these like 95% type statements of work in discrete choice makes the following assumption, which is this independence of relevant alternatives. And this is a bit of a fudge definition because I'm kind of setting aside some regularity conditions about like assuming that probabilities are positive. Quickly, you'll see that you get divide by zero errors if you start doing that with what I'm doing here. But by and large, you can think of IIA as the following assumption. It's the idea that the ratio between the ratio between X and Y, which is sort of this quantity here, stays the same no matter what other alternatives C the choices are being made in the presence of. So I can pack the set full of things, and that's not going to change the ratio with which you choose X to Y. So a consequence is the ratio between X and Y stays the same no matter what you're adding to the choice set. And this is an axiom that Luce started a lot of the work in discrete choice by kind of throwing down in this monograph length treatment from 1959. And one of the powerful things with assuming IIA is that it immediately implies or admits what Luce calls a ratio representation, which says that when you're choosing elements from a set, really if you assume IIA, that is equivalent to a model where each of these little probability distributions is a probability that's defined by sort of like the proportional to some notion of utility or strength, that there's some gammas for every element, positive quantities, non-negative. I'm going to sort of, there are particular like pathologies you need to handle if you're going to allow for things to be 0, but bear with me and just assume things are positive. And you're just kind of picking things proportional to how strong they are. So you throw down 3 elements and you're going to pick them proportional to some inherent quality for all subsets. You can sort of like, you can see pretty quickly that you know, the denominator here is just a normalizer. And so any ratio like this, you're going to just get gamma x to gamma y. And in any set, you're just going to kind of, the denominator is going to fly away and you're just going to get gamma x to gamma y. Okay. So some examples where this arguably doesn't hold. It's sort of easier to narrate around that. It's a reasonable thing that, you know, items have inherent utilities and you pick things proportional to their utilities. So doing a little bit of a history lesson, De Brugge, who's a prominent 20th century economist, was charged with doing a book review of Luce's 1959 treatise. And he says, oh, this independence of relevant alternative assumption that Luce introduces, it's a nice one, but it clearly doesn't hold because of the following important choice in my life, where he talks about, you know, if you're choosing between listening to a recording of Debussy or Beethoven's, you would, you know, you might choose Beethoven, and then you add another item to that set, which is another recording of Beethoven. You know, this is the LA Phil versus the New York Philharmonic. And in that larger set, it's pretty clear that it's not just, you know, introducing that third alternative is not going to steal proportionally from the other 2 alternatives. It's pretty clear that, you know, you probably have strict preferences over recordings of Beethoven's 8th Symphony. And, you know, you're only going to pick one of those 2. And you're not going to sort of like steal proportionally from the 2 different alternatives. That's like the literal example that De Brugge goes on about in his book review. Now, much more recent work, there is evidence that in sponsored search advertising, when you show bundles of ads, there are click-through rates, particularly when you consider an outside option. So Sid's question is very on point here, that in a lot of these settings, the outside option is not clicking on an alternative. And so the no-click alternative is sort of always an alternative sitting in a lot of these sets. The click-through rate of ads depends in subtle ways on what's sometimes called like the group fitness, or sort of like the group performance. Austin has done great work at Google on sort of like the, this is great paper title and also a good paper, but on the relevance of irrelevant alternatives, a good play, which showing that when some people are navigating here in this example, restaurant choices, there's a nested structure, there's reasonably a nested structure on how they're making these choices. That nested structure is fairly similar to the nested structure that explains the violations of IIA in De Brugge's example, but sort of like seen to play out in data. So, okay, so it's pretty clear that, you know, things like nested decision-making or overall kind of like a lot of the search ads violations are driven by a theory that like, oh, well, like a good ad draws your attention to the ad box. For those of you who are in the ad, like online sponsored search ads world, you know that these sidebar ads no longer appear. To find an example of one, I have to do like a Google image search as opposed to screenshotting something. So search is a rapidly changing, search ads is a rapidly changing game, but it's nonetheless the example that's studied in these 2012 and 2014 ancient history papers in the dog years of sponsored search ad research. Okay, so IIA doesn't always hold. We're going to come back to at the end of this talk about how that's a tricky question to tell whether you're actually in IIA or not. But for now, I'm just sort of like setting up examples that are common discussion points. An interesting thing about IIA is that if you go back to this simplex view, you had sort of an example here on the left of the pairwise and triplet-wise choices. You can think of IIA as sort of like once you've sort of fixed one of the pairwise probabilities, it actually places a lot of constraints on all the other choices. So the since you've fixed the proportion of A to B, it means that within the triplet probability, you have to sort of like live along this line. And then furthermore, if you live at the yellow point, that actually fixes the proportion of B to C. So the color bar is sort of fixing what the other probabilities are as a function of this one thing. So you're sort of like IIA, you spot one pairwise probability and you've quickly collapsed everything that can happen a lot. There's only sort of 2 degrees of freedom, if you will. And furthermore, if you fix the triplet probability, you've just fixed all the pairwise probabilities. So IIA is a very strong constraint, and constraints make powerful models, right? If you have a simple model, you can get a lot of power out of it. It's much faster to learn, etc. So IIA, I could give this whole talk and just kind of talk about axiomatic discrete choice, but it's also the assumption that underlies the multinomial logit model of discrete choice. It's sort of, all I've done here is I've taken the ratio representation of loose and I've written it in terms of a sort of an exponential. So I've exponentiated the gamma x here is, in my earlier slide, is this term on the top, which is now sort of like, that is equal to gamma x. I'm just gonna, I don't want to make my slides too kludgy. And the multinomial logit is sort of a major workhorse in modern machine learning. Robots are taking over, et cetera. Importantly, standard sort of statistical, there's a long history of work in categorical, there's great textbooks from the 80s and 90s on categorical data analysis, a term of art that's fallen out of favor, where you say that the utilities are sort of linear in some features, and then that's sort of just a generalized linear model. For those of you who are active on Twitter, there's this hashtag that grew up, sort of started being chatted about a month ago. Danielle Witten at UW started talking about how everything, it's just a linear model. How a lot of people put a lot of fancy window dressing on models, but IJALM. So if you search Twitter for that, you'll see a bunch of discussions about people talking about how all sorts of fancy models are just linear models. Okay, so that's the independence of relevant alternatives as a set of constraints over models. Now, Luce got there with an assumption, sort of axiomatic approach. What I'm going to do now, and sort of the main focus of the remainder of this talk, modulo time saved at the end to talk about hypothesis testing, is kind of derive IIA or derive the multinomial logit in 3 different ways. And each of those ways gives a perspective on how you can relax IIA that I think is interesting. And so the 3 different ways we're going to talk about this, to sort of derive MNL, is we're going to derive it via random utility model, which this is a derivation that's included in sort of a standard econometrics graduate course. Then we're going to talk about other random utility models. Next, I'm going to show you a result which was really my gateway into this world of probabilistic discrete choice, which is a paper that shows that it was a paper about an algorithm, but it shows that MNL is closely related to a Markov chain. Then I'm going to show you that that's just one way to Markov chainify discrete choice, and that there are other Markov chains that are attractive and have attractive properties for modeling discrete choice. Finally, I'm going to talk about a third perspective, which is that you can think of IIA and its corresponding model, MNL, the multinomial logit, as the first order truncation of this original object, the choice system. And this is an observation that dates back to the marketing literature in the 80s. And that means that there's, if you're going to talk about sort of an expansion or a basis, why stop at first order when you can go to the second order or third order, et cetera? So I'm going to talk about that as sort of an interesting way to think about models that step just beyond IIA, keeping models sort of parsimonious and therefore also powerful. And all 3 of these perspectives all kind of can all do IIA, they can all do MNL. I'm going to explicitly set aside, this is a comment that's not so relevant for those of you who haven't seen this literature, For those of you who have, you should be able to recognize that I'm doing it an injustice by not talking about explicit mixture models. So there's a large literature in the discrete choice on mixture models in the same way that you have mixtures of Gaussians, you do mixtures of Logits. There's also a lot of work on nested Logit models, including Austin's and a long line of work before it. I'm going to sort of set that aside as more standard perspectives where sort of like this like you're not it's a different, you don't get the same kind of like collapse thing. I mean, if you do a mixture model and there's only one component, yes, you have a Logit model. But I'm going to talk about these sort of like 3 different ways to derive. You could, in the same way that you mix Logits, you could mix Markov chains. So it's sort of a orthogonal, if you will, question of sort of thinking about mixtures. So random utility models. We want to think about how people are making choices from sets. Well, what if we let each of these schools, each of these travel options, each of these digital cameras, we associate a random variable with each one, and that's going to be our random variable here up top. And that is sort of just xi, and it has some mean, and then we're going to talk about a zero mean, generally speaking, zero mean noise term. And then what we're going to say is that, there's these 5 elements, and the probability of choosing an element from a set is going to be just the probability that that's the max element. So what that means is that, if your set is these 5 things, it's what's the probability that each element is the max? Well, it's probably the purple thing, but then sometimes blue is going to win with a certain quantifiable probability. Very seldom sort of blue is going to be in its left tail, purple is going to be its left tail, and green's going to win. And then gray and orange are kind of really out of the money in this problem. So you can write this down for any set of distributions sort of on the real line, any set of random variables. And it turns out, and this is the result that's sort of a standard derivation in econometrics, if the noise terms are independent zero mean Gumbel, also known as the double exponential or extreme value distribution type 1, you get MNL. You get that you sort of work out the math. What's the probability that xi is the max? It's proportional to these sort of exponentiated means. Now, the thing about random utility models is that they don't need to have independent noise distributions. They don't even need to have the same family. Here, I'm just showing you a bunch of Gaussian seeming noise distributions with different variances and different means. The larger space of random utility models is very, very, very large. What I haven't even shown you in this illustration, because I'm not very good at visualization, or this type of is, you can have correlations between these random variables. They need not be independent. And that's a part of the literature. And the literature on random utility models has been very successful. And only one very specific set of assumptions gives you MNL. Because, yeah, so here's an example of something that you might have heard of that can be thought of as a random utility model, and will illustrate why random utility models are weird. Or they're not weird. I mean, weird is good. A curiosity, we'll say, about random utility models. So the curiosity has its origins in what's sometimes called non-transitive or intransitive dice. Now, this is a great parlor trick. I used to have a set of intransitive dice that I would bring to the occasional lecture where these types of things would come up, and I would have loved to hold them up for you. But I foolishly kind of like left there, like people were playing with them, and then I walked out of the lecture hall and then they went missing. So I need to get myself a new set of intransitive dice. But the basic idea of non-transitive dice, it's an observation that dates back to the 50s, sometimes called the Steinhaus-Tribula paradox, is that you can have 3 random variables, or to make things really concrete and simple, you can have 3 dice that are independent distributions. They're not identically distributed, but they're independent. And each one, basically the pairwise win probability is non-transitive. So what does that mean? If Austin picked up the red dice and I picked up the green dice, and we were sort of playing to win, sort of playing high dice, well, in a random utility model, we'd be saying like, what's the probability that I win? Well, it's sort of like governed by the outcome of this die roll. And so the question here, you can work out this math in a discrete distribution. You can say, okay, so like the red dice, when it's a 9, it's going to beat everything the green dice is going to throw down. So first of all, there's 9 different possible outcomes. And the 9 wins all 3 of its. The 4 wins 1 of its. The 4 wins if green throws a 1. The 2 wins if green throws a 1. So in total, there's 5 out of 9. So, red beats green 5 out of 9 times. And similarly, there's sort of this non-transitive cycle where the victory probability is greater than a half all the way around. This is super fun when you look at dice like this. And there's a whole line of research led by a bunch of curious characters like Joel Spencer, or not led by, but which has seen cameos from people like Joel Spencer and Ron Graham on sort of like, what happens if you have n dice and how large can you make this cycle, and sort of various discrete probability questions that are really fun that people have worked out. And there's modern review articles that you don't have to go back to the Stein-Ostrobula article. You can kind of just do a Google Scholar search for non-transitive or intransitive dice synonyms. But the important thing I want to show you here is that sort of rums, even when they're independent, they need not be stochastically transitive. And so just as sort of a very small pointer to some of my own work, I'm situating it in sort of a big literature perspective here. There's this paper with this student that was sort of came out of a course project, which shows that transitivity as an assumption makes certain assumptions on the concavity of the log likelihood in sort of probabilistic. If you're trying to do maximum likelihood, having a convex negative log likelihood is important, or is useful. It's not the end all of inference, but so there's sort of there's a bunch of fundamental questions about how easy something is to learn that connects to stochastic transitivity. That said, that's a subtler point than you might appreciate it as, unless you've been in this world. So it's really a bit, convexity and concavity is about the parameterization, and it turns out that it's really about the sort of independent parameterization here. But I'll sort of like give that as a pointer and defer to the careful wording in that work. Okay, so what types of choice systems or conditional choice systems can rums represent? This is an area where there is a beautiful theorem from the 70s. And the theorem says that a random utility model can realize a choice system if and only if and now you should be sort of like you should sort of be wondering, what is this thing? If the Bloch-Marshak polynomials of the system are all non-negative. So the Bloch-Marshak polynomials are polynomials due to Bloch and Marshak. They're actually not even polynomials. They're linear functions, but they get called polynomials because I guess they are polynomials. But what these assumptions say, and sort of it's Bloch and Marshak. Marshak was a prominent 20th century econometrician, or sort of the first president of the Econometric Society, founding whatever. And they showed if, and Fallmain showed only if. So that's why Fallmain gets credit for the characterization theorem. So what these polynomials are is they say that first, all the probabilities have to be positive. Okay, that's an easy one. Next, all of the probabilities have to obey the following inequality, which is that if you remove an element, the probability doesn't go up. Right, so the probability, this is a certain probability here of X from C, and then we dropped Y, and that means that the probability of X, could only go up. If you remove things, if you remove items, alternatives can't get less likely to be chosen. You've reduced the competition, things can only go up. That's what regularity says. It's sort of a monotonicity property in choice systems. And all rums have to obey regularity. The Bloch-Marshak polynomials go on to set additional order 3, up to order n sort of constraints, and all those polynomials, waving my hands, they're not polynomials, or they're linear, have to be greater than 0. And that's actually a huge amount of constraints. So what does that mean in the simplex view? In the middle, we have these IIA constraints that we saw. The RUM constraints end up kind of like setting up this interior polytope that if you spot the pairwise probability, the triplet probability sort of can't go outside of these two wings. And if it's just 3 elements, it's really just regularity that's going on, that you can't, the triplet probability is can't be too different than what the pairwise probability says. It's sort of upper and lower bounded by the 2 pairwise probabilities. So that's RUMs that are kind of, there's the IIA RUM if you make this assumption about Gumbel. And then there's, you can choose other noise distributions. And that's sort of been a traditional way to deviate from IIA in discrete choice. Now I'm going to switch to the second perspective. So it turns out that consider the following modeling problem. You're choosing between digital cameras, and you're staring at a digital camera, and you're you're staring at that red one, and you're like, oh, that's nice and small. Oh, but actually, you know what? That the lens on that purple one is really big. So there's you switch to that one in some mental, your eye is jumping around the option space, and then you're like, oh, yeah, that's actually just kind of like a very similar, also Nikon, or sorry, the Nikon, well, Sony has an equivalent model, I'm going to consider that one. And then you're like, no, wait, the red one's really good because it's small. And so, your eye is jumping around this state space very much like a Markov chain. And a subtle point here is that I'm going to write this model of how you make choices down as a continuous time Markov chain, not a discrete one. And that turns out to be the natural language for this problem. But essentially, what if we wanted to model this probability distribution over a triplet based on the stationary distribution of some pairwise Markov chain? So you're jumping around and you're and what's the stationary distribution? So this is a general model that is parameterized by some rate matrix Q. And that places a distribution on the set. And the way that we're going to let this Markov chain define a choice system, for all subsets, is that we're also going to talk about the restriction to subsets and say, oh, if there's only 2 elements, then the Markov chain is just like the Markov chain on the submatrix of Q. So now, it's the same, it's these 2 elements here, I've just dropped them here, and the purple camera disappeared. And what you should see, what you could see if you start at this for a bit, is that the purple camera up here is really stealing asymmetrically from the red camera versus the black camera. Depending on if you're standing here or here, if you're in the red camera, you're really likely to jump to the purple camera. The edge weight here is supposed to indicate some rate intensity. And so these larger Markov chains can create all sorts of asymmetric stealing, which is the essence of violating IIA. But it turns out that, all right, so we're going to call the set of stationary distributions defining the choice system, parameterized by this single matrix Q. It turns out that if you let the rates only depend on where you're going, so you say that this jumping process is only defined based on the target, then the choice system satisfies IIA. And so then you get that you can think of IIA or the MNL choice model as a specific type of Markov chain that has a very simple n-dimensional parameterization, or n-1 out of n squared parameters. Now, this observation came out of this work by Mishra and Grossglauser, which was a NeurIPS 2015 paper. And what they were actually doing is that this is I think, beautiful paper. They were trying to come up, they came up with an iterative spectral algorithm to learn MNL parameters. And what they showed was that the stationary point of the MNL likelihood, so it's an optimization problem that has stationary points, those points are the same as the stationary distribution in the limit of a sequence of Markov chains. And the reasoning is this contraction mapping in the space of Markov chains. And it's quite a subtle argument that's quite surprising, because it's not just quite one-to-one as a learning problem. The model is one-to-one, you don't need to have this many Markov chains, but to learn it, you need a sequence of them, which is why it's an iterative spectral algorithm. And so after that paper came out, Stephen Reagan and I were sort of working on discrete choice and sort of spotted that, well, wait a second, they're using that as sort of like the motivation for their model, but there's this much more general Markov chain. So I had this paper at NeurIPS the year that followed that sort of talked about how, you know, there's this more general class of Markov chains here that can do things that RUMs can't. That said, likelihood maximization is non-convex and clumsy here. And the fun thing here is that there's been this sort of a mini explosion of people who are taking kind of Markov chain approaches to discrete choice. So if I'm going to trace origins, I would actually say that there's this very, very nice paper by Negahban, and Shah from 2012 called RankCentrality, which connects, you know, Markov chains are about random walks. And what it does is it says, if you have pairwise comparison data, if you take a random walk on the comparison data, the stationary distribution looks a lot like the quality parameters of a discrete choice model. And here's where there's a sort of point of history that they were studying a discrete time Markov chain. And because of that, they needed to do a lot of regularity assumptions. If they had only set up the continuous time Markov chain, they sort of would have gotten the learning problem right. But the RankCentrality paper, it'd be interesting to see how they would rewrite it if they kind of took the continuous time perspective, because that was what happened with the Mishra and Grossglauser paper. There is actually a Markov chain inside this old paper on ad preferences that I've been meaning to kind of like diff it against the other models in the literature. It's a good problem for somebody interested in applied problems involving Markov chains to take that that Markov chain model and sort of line it up with the other models in the literature. There's also other work here that I'm realizing I left off on, like random walk rank, which is how different ways to rank things using random walks that sort of like doesn't quite make the choice connection, but there is one. Blanchet, Gallego, and Goyal, sort of a Columbia team, though Jose recently moved to Stanford, Jose Blanchet. They had a different Markov chain model of choice. And then there's this more recent paper here is actually a neural net on top of a pairwise choice Markov chain, which I thought was hilarious, because why? Of course, somebody put a Markov chain in a neural net, but these pairwise choice Markov chains, they're interesting because they don't need to satisfy regularity, and RUMs do. And you know, if you, just from a curiosities about the space of choice systems, it's interesting to think about what different models can and can't do. So it can do things that RUMs can't. In the axiomatic world, there's something called uniform expansion that we showed in their work that all pairwise choice Markov chain models satisfy. And that plugs in a fun way, because Yalot showed that in RUMs, in random utility models, uniform expansion implies IA, but pairwise choice Markov chains are not RUMs. So that's where they're kind of this curious, they occupy an empty quadrant in the space of choice models, because they satisfy this uniform expansion property without being RUMs, and therefore without that implying IIA. I was not an axiomatic discrete choice person before we started that work, but I thought it was like a very nice way to complete the square in terms of missing terrain. Here is like, there really is this, somebody went and like put a Markov chain stationary distribution as a subroutine within a neural net. I sort of say kids these days, because when I was in grad school, neural networks were not a part of graduate machine learning coursework. It's, you know, I'm well aware, I've been following the neural net literature, surely, as I'm sure most other people with an interest in sort of solving problems have, but it's just sort of interesting to see somebody go do that. Okay, so the third perspective that I'm going to focus the remainder of this talk on, or the remainder of the talk, is on this truncation perspective. So we're talking about 3 different ways to get to IA and 3 different ways to work outside of it. So we're going to go back to this universal logit model, this arbitrary choice model. And the reason why McFadden's universal logit model gets called the logit is that he kind of puts an arbitrary model in a logit shape. So really what we're just saying is this first, the important bullet point is the first one, which is that items have utilities in sets, and then there's a normalizing constant that's actually not going to be that relevant. That just kind of like kills some degrees of freedom, because it's sort of equivalent to saying that the probability distribution has to sum to 1. And so here we have an arbitrary model, which just says that the probabilities are proportional to these utilities, which is sort of like saying that these things are arbitrary, the probabilities are arbitrary. And the following is an expansion that Batzel and Polking showed is sort of they showed a way to define a unique expansion, which says that, well, let's say that what's the utility of X in the presence of C? Well, there's an inherent like item level utility, call it V. That's this term. Then we're going to say that there's this second order term, which is the utility of X in the presence of every item. That's sort of like items have a push and pull on each other. Then we're going to say that pairs, sort of like if there's both chips and guac, then salsa does something. That's a separate phenomenon from how chips pulls on salsa and guac pulls on salsa. Sort of there's some pair thing, and then triplet thing, and sort of there's a series expansion here that goes all the way out to sort of the Cth order. I'm not showing you some constraints that kind of pin this down, but basically they wrote this down and then said, what if we just sort of like start looking for truncations? This was sort of Batzel and Polking's work as looking at choice as a marketing problem in the 80s. And so we're going to call the pth order model, sort of like the truncation at the pth order. We're going to call that MP, and we're going to notice that these are all nested models. Now, the first order model is MNL. It's saying that items have inherent utilities. And that satisfies IAA. The full order model is the universal logit, and the fun stuff happens in between. There's sort of like this opportunity to step outside MNL, but in minimal parsimonious ways. So what does that look like? So if you look at just the model that allows for pairwise interactions between items, you get sort of M2. You do some manipulations and you get that the choice probabilities are affected just by these pairwise effects of how X affects Z. And then there's also normalizing, there's sort of like push and pull. Every alternative X is being pulled or pushed by every Z in the set. Sid, I hear your audio. Is that an incoming question? No, maybe it's not. Okay. You can think of this as a pairwise dependence of relevant alternatives. The fancy thing here is that up until coming up with this, encountering this model in our own work, sort of thought that there was some fundamental connection between being able to have a convex likelihood and violate IIA. And that's not true. And this is sort of a true counterexample, because here's something, it's convex in its use, and it can clearly violate IIA in very strong ways. You can do a matrix factorization of U, because U is this sort of n squared object, and you can say that items have target vectors and context vectors, and I won't really spend time on that. So I said that this was an idea that dates back to Batzel and Polking in terms of these like second order models. They were actually they wrote down the model and then they did a least squares fit. So the main contribution of my own work on this sort of type of problem is that actually you can actually do direct maximum likelihood using the optimization math that's come out since 1985. It turns out that you don't need to just kind of like draw a least squares fit. You can kind of show that if you do gradient descent on that likelihood, you can, the expected loss is upper bounded by a quantity that sort of like decreases in the size of the data M. This is a fascinating subliterature because starting mainly with work by Nihar Shah, now at Carnegie Mellon, these upper bounds, they depend on the following funky quantity, which is the algebraic connectivity, the second eigenvalue of a Laplacian constructed from the data. And that dates all the way back to sort of work by Ford on identifiability conditions. And it says that there's something about the cut structure of how items are being compared that is fundamental to how quickly you learn the model. And that's been that for me was just really beautiful. So some of those ideas are, Nihar Shah's work established the role of this, the comparison Laplacian in MNL. And here we're sort of showing that we can do the same thing for this pairwise interaction model. This analysis is for the full rank case, but the full rank bound applies to the low rank model. We actually kind of like, as a convergence theorem or uniform convergence theorem, it connects to the blade chest model that's a work out of Cornell with Torsten and his PhD student, Shu Chen, and also many word-to-vec type models. We've expanded this, we've extended this squared error, expected court squared error bound to a tail bound if you're sort of one of the people who thinks about that, but I'm not going to go into that. So to sort of conclude, because with apologies that I'm not going to get to talk about the IAA testing, the hypothesis testing result, which is of a very different flavor that I think you would all be out of energy for anyway, and would have to sort of be the subject of its own talk in its own right. And actually, Arjun Seshadri has a great talk on YouTube about that work if you're curious about it. But basically, we've talked about 3 different models of discrete choice that all step outside of assuming IAA in different ways. And you can throw down different types of noise distributions and get some generalized RUM. You can look at these not simplistic Markov chains and get an interesting model of choice. Or you can do these pairwise interaction models that have a very clean sort of machine learning value because of their maximum likelihood being, or the negative log likelihood being convex. There are results that look good, but that's not really what this talk is about. I sort of wanted to talk about the mathematical object. So this is this context-dependent model where this is the negative log likelihood. CDM is our athlete having a low, lower is better. The x-axis here is sort of looking at various rank matrices. A fun thing about the CDM is that it's, like I alluded to the connection to word2vec. You can think of it as having embeddings. This is embeddings in a triplet data set. And that's sort of where I'm going to end. Now I need to figure out how to skip to, I'm just going to do the embarrassing thing where I admit that I had more material than I wanted to cover, and I go to the summary. Choice systems are beautiful things, and there's been very recent work on opening doors to other ways to deviate beyond IAA. The testing work sort of replaces an ambiguity in the literature with rigorous pessimism and shows that testing IA is very hard in traditional kind of high dimensional ways. So thank you.
All right, I'll clap for everybody. Thanks, Johan. So we have time for a couple of questions if people want to use the raise hand feature in Zoom. John has a question.
Yeah, so thanks. That was a great talk. Very, very interesting. So in a world where I think about, sort of the relation of choice to ranking, like, so if I think about rankings as distributions over permutations, what's a good way to think about sort of the connection between sort of choice functions and rankings?
Yeah. So the like random utility perspective on ranking is dates back to the Plackett-Luce model, which is sort of Luce was involved as sort of a choice person. And it's saying that there's a random utility model formulation where you just say, you realize all the random variables, and then you put them in sort order. And then that induces a distribution on permutations. And that's sort of one natural formulation. That is equivalent to there's a notion of distributions on rankings on permutations that's called L decomposability. There's this paper by Critchlow in 1991 that's often cited, which is that which distributions on SN can you decompose as a sequence of choices? So you want to say first you pick one element from the set, set it aside. And that's a discrete, that's a probabilistic choice. You pick another element from the set, you set that aside. Pick another element from the set that aside, and you line up your ducks and you get a ranking, and that happens with probability, whatever the probability is. And that, if you do those choices according to an MNL, or sorry, according to a Gumbel, an MNL on the choices, you get the Plackett-Luce model. Or if you do a random utility model of rankings and you do the instantaneous realization, if those distributions are Gumbel, you get MNL. Or you get Plackett-Luce. So those two perspectives are equivalent. You're maybe baiting me, but the NeurIPS decision deadline is in 5 hours or whatever, and we have a paper under review on rankings that's specifically about applying these like pairwise interactions between items and ranking, including in sort of like ranked choice voting and other contexts. But I'm happy to share that preprint at any if you're interested. But yeah, it's most of the modeling in SN is very simplistic, like Mallow's type models or this Plackett-Luce model, and both of those are very single peaked as a distribution in SN. Whereas you can do more complicated things. You can either make explicit mixtures, or here we can do sort of like more organic, complicated things.
Thanks.
All right, so let's take one quick question from Kieran.
Yeah, hi Johan, thanks for the talk. I had a question about the truncation view and about likelihood convexity. So if it seems kind of nice that when you do the second order truncation, you can do the simplification that leaves a convex negative log likelihood. I guess that if you did a third order truncation, things would get messier and then you would no longer have that convexity. Is that the case?
You should still, so if you don't do any tensor factors, it's going to be a tensor model. It's going to be parameterized by sort of a tensor of interaction terms. If you don't do any tensor factorization and you let it live in its like n cubed parameterization, you should be convex in that. Now that starts to be a crazy decision if you're not going to factorize that. And so as soon as you're factorizing it, you're not just facing the hairiness of matrix factorization, you're facing the hairiness of tensor factorization. So that makes me a little bit afraid. But it's a good question, like how parsimoniously can you do that? So we only have like convergence stuff. This was work driven by Arjun Seshadri, who I think managed to sneak onto this seminar. So he's somewhere in the audience. But so hi Arjun. But we only have sort of the convergence results for the unfactorized version. The factorized version, there's a lot of things happening in matrix factorization right now. And you can think of this as like not the Frobenius loss, not like a non-standard loss on matrix factorization. We were sitting on like a U they were trying to factorize. And it's like some of the existing fancy new work on matrix factorization almost gives us that the factorized version is unique, or that we like converge to the global optima, but not quite. But I would be very surprised if something like that extended to tensor factorization methods, given just the general delta between matrix and tensor factorization.
All right, great. We're running a little into overtime, so how about everybody unmute their mics and clap for Johan. And as always, well, now in our virtual world, we have our reception on gather.town. The link Erica posted in the chat in the Zoom, and hopefully everybody has it in their email inbox as well. So we'll see you there.
I'll be by the purple couches.
All right, thanks, Johan.
Cheers, Austin. Thanks.